A very good morning, dear students. In this video I am going to explain about the last type of electron displacement effect, that is known as hyperconjugation. So in last videos we have seen about the first three displacements effect, that is inductive effect, mesomeric effect, and next one electromeric effect. Now I am going to explain about the topic hyperconjugation. It is also a type of electron displacement effect. So this can be seen, okay, it is general stabilizing effect. Okay, it is a stabilizing effect in which sigma bond electrons of carbon hydrogen bond. Okay, see here which type of bond? Carbon hydrogen bond. Sigma electrons are partially delocalizing. It's not completely, partially delocalizing. See which type of electrons? Sigma bond electrons. They are locating between carbon and hydrogen. So carbon and hydrogen connected by a single bond, right? So that single bond is now containing sigma bonded electrons. Now such sigma bonded electrons partially participates in delocalization, that is displacement takes place when adjacent pi bond or unshared p orbital is present. Okay, that means if it is with adjacent pi bond or unshared p orbital electron, so then only the displacement of electrons takes place between carbon and hydrogen. Understand? In this effect, sigma bonded electrons of carbon hydrogen bond are in conjugation with the system. Okay, are in conjugation with the pi system or pi electron system or unshared p orbital. That means whenever the sigma bond is in pi bonded system or it is in conjugation with the unshared p orbital system, then only the delocalization of electrons will takes place. It is known as permanent effect. Okay, it is known as permanent effect. See here, hyperconjugation is only due to delocalization of sigma bonded electrons between carbon and hydrogen. Between carbon and hydrogen, whatever sigma bond is there, that sigma bonded electrons involves in displacement. When it undergo displacement, if it is in conjugation with pi bond or unshared in the sense the electrons which do not participate in a bond, those are known as unshared. So either when it is in a conjugation with pi bond or sigma unshared pair of electrons, okay, then that type of system is present along with the sigma electron, then this sigma electrons involves in delocalization. Okay, and this effect is known as permanent effect. This effect is known as permanent effect. So now examples these two. Okay, so carbon hydrogen is now with sigma bond and it is in conjugation with pi bond, pi system. Single bond, double bond, single bond. What is meant by conjugation? If alternative pi bonds and single bonds are present, that is known as conjugation. Sigma, pi, sigma. Double bond, single bond, single bond. Okay, now your conjugation is present. So the carbon hydrogen sigma bonded electron should involve in delocalization. See, the more the hyperconjugation, whenever more number of hyperconjugation structures are possible, greater will be the stability of alkene. It can explain about the stability of alkene. What is alkene? It is a hydrocarbon which contain at least one carbon-carbon double bond. Then that is known as hyperconjugated structure, that is known as alkene. Okay, a hydrocarbon which contain at least one carbon-carbon double bond, then that type of system or compound is known as alkene. Understand? So when it becomes more stable, if it is having more number of hyperconjugation structures, then the greater will be the stability of alkene. Understand? Example, butadiene. Okay, butadiene is more stable than butene. Butene means it is one butene. Okay, here double bond is present at first position, but here double bond is present at second position. So this is more stable than this because it will be containing more number of hyperconjugation structures. Whatever the compound is with more number of hyperconjugative structures, that will be the more stable. Understand? Now we'll see that hyperconjugation in the system. So this is known as propene. Why it is propene? Okay, why it is propene? Because 3 carbon atoms are present and between first 2 carbon atoms double bond is located. So we can call it as prop. Prop is word root for the 3 carbon atoms and suffix is -ene. Why it is containing suffix -ene? Because of having double bond between the 2 carbon atoms. Understand? Now remember, all carbon hydrogen sigma bonds do not involve in delocalization. Only carbon alpha hydrogen, okay, carbon and alpha hydrogen bond, sigma bond involves in delocalization. We'll see what is that alpha hydrogen. Okay, alpha hydrogen is a hydrogen present on alpha carbon. Alpha hydrogen is a hydrogen present on alpha carbon. First we want to know what is alpha carbon. Okay, alpha carbon is a carbon present adjacent to the functional group, okay, or substituent, or if it is present on adjacent to the double or triple bond, then those are known as alpha carbons. Okay, see here, listen carefully. So alpha carbon is a carbon which is present adjacent to the double bonded carbon. So now this is double bonded carbon. Even this is double bonded carbon. Adjacent to this double bonded carbon, whatever the carbon is present, that carbon is known as alpha carbon. That alpha carbon, whatever the hydrogens are present on that alpha carbon, those are known as alpha hydrogens. Now this is alpha hydrogen, this is alpha hydrogen, this is alpha hydrogen. Alpha hydrogen is a hydrogen present on alpha carbon. Alpha carbon is the carbon present adjacent to the multiple bonded carbon or functional group carbon. Here there is no functional group, only multiple bonds are present. So this is known as alpha carbon. Alpha carbon mele iro hydrogens matrane navu alpha hydrogens anta consider madbeku. This hydrogen is not alpha because it is directly located on double bonded carbon. Okay, this is not alpha carbon, so this is not alpha hydrogen. So hydrogen which is present on alpha carbon, that is known as alpha hydrogen. Okay, now the number of hyperconjugation structures always depends on the number of alpha hydrogens. Okay, number of hyperconjugation structures depends on number of alpha hydrogens. See, in the first step, pi bond moves to this carbon atom. Okay, then that carbon gets negative charge. Then upon this carbon, valency reduces. So that I am writing this structure here to understand easily. Okay, same structure I have written here for propene. So initially what is happening? Pi bond is moving to this carbon. Actually this carbon is with 4 bonds. 1, 2, 3, 4. Now one of the bond is moving this side. So it becomes one less valent. So whatever the bond exists between the carbon and hydrogen, partially that moves this side. Okay, then there is no bond between the carbon and hydrogen. Then we will get the first hyperconjugative structure. See, first write hydrogen. There is a bond between carbon hydrogen and there is a bond between carbon and this hydrogen. Now here hydrogen is present, but there is no bond between these two because that bond only shifting between these two carbons and making double bond. Understand? Now whatever the double bond exists between these two carbons, that becomes single bond, and this carbon with 2 hydrogens, that I am writing here. Okay, now this is getting extra electron, so it will be having negative charge, and hydrogen here losing electron, so it will be having a positive charge. Understand? Again it participates in one more hyperconjugative structure because another alpha hydrogen is available. So whenever this carbon hydrogen sigma bond moves here, okay, then between carbon and this hydrogen bond is created, and between these two there is no bond. Then we will get another hyperconjugative structure that I am writing here. See, hydrogen is there, no bond between these two, so I am writing like this, and down to that one hydrogen is present, and here one new bond is formed between these two. Now double bond as it is, single bond carbon, single bond carbon, 2 hydrogens, okay, 2 hydrogens, and now here negative charge. This hydrogen is losing bond, so it will be having a positive charge. Okay, now one more alpha hydrogen is available which is present adjacent to this. So even it participates in delocalization. Now this carbon and this alpha hydrogen sigma bonded electrons involves in delocalization. Okay, between these two carbon and hydrogens. Then we will get another resonating structure. Okay, see. First write this hydrogen. Now a new bond is made between carbon and hydrogen. And here one bond is created with this. Now here there is no bond between these two. So hydrogen. Understand? Now here double bond is present and single carbon is present. Single bond with carbon and two hydrogens are located here. Due to taking electrons, it will be having negative charge. Because of losing electrons, this alpha hydrogen is now with positive charge. Clear? Now with this the number of alpha hydrogens are finished. No more alpha hydrogens. So finally what happens? To neutralize this positive charge, whatever the pi bond exists between these two carbon atoms will move here and make a bond. Then to neutralize the bond, to neutralize the valency on this carbon, this negative charge will make a pi bond here. Okay. Then what we will get? C. Okay, two hydrogens on this. I have represented these two. Negative charge is making double bond here. Double bond already existing. Carbon with hydrogen is present. Whenever this pi bond moves here between these two carbons, only single bond is present. That single bond is already represented. Now on this carbon atom, three hydrogens are present with the sigma bonds that already we got. So it leads to give finally the first structure. Okay, so in this case, this one and this one and this one, these three are considered as hyperconjugative structures. So this is not the hyperconjugative structure. So how many hyperconjugative structures are possible here? Totally 3. Why only 3 hyperconjugative structures are possible? Because of containing 3 alpha hydrogen atoms. Okay, whenever number of alpha hydrogens increases, number of hyperconjugative structures also increases, thereby stability of alkene also increases. Understand? So that's why but 2-ene is more stable than but 1-ene. We'll see why but 2-ene is more stable than but 1-ene. I am taking here but 2-ene, that is CH3, CH double bond, CH bond, CH3. Okay, this is called but 2-ene. 1, 2, 3, 4. At second carbon double bond is present, so but 2-ene. Next butene I am writing CH3, CH2, CH2, sorry, CH double bond, CH3. This is called but 1-ene, which is also known as butene. Okay, now see number of alpha hydrogens in these two compounds, because more number of hyperconjugation structures are possible only with the more number of alpha hydrogens. What is alpha hydrogen? A hydrogen which is present on alpha carbon is known as alpha hydrogen. What is alpha carbon? The carbon which is adjacent to multiple bond is known as alpha. So this is multiple bond and this is multiple bonded carbon. Adjacent to this carbon is present, so it is called alpha carbon. And even this is adjacent to this double bonded carbon, even we can consider it as alpha carbon. Now these two are the alpha carbons present in but 2-ene. On this first alpha carbon, how many hydrogens are present? 3 hydrogens. On this 3, total number of alpha hydrogens are 6. Okay, this is containing but 2-ene containing 6 alpha hydrogens. But on but 1-ene, so this is first carbon. Okay, this is multiple carbon. Adjacent to this there is no more carbon, but adjacent to this there is a carbon. So this is alpha, this is beta. Now we want only about alpha carbon. Upon alpha carbon, how many hydrogens are present? 2. Now these 2 are the alpha hydrogens. On but 1-ene, only 2 alpha hydrogens are present. Okay, that means but 1-ene is with only 2 alpha hydrogens. It can give only 2 hyperconjugative structures. But but 2-ene contains totally 6 alpha hydrogens. So number of possible hyperconjugative structures are also 6. Whenever number of hyperconjugative structures increases, stability also increases. That's why but 2-ene is more stable than but 1-ene according to hyperconjugation. Okay. Now stability of carbocation also we can explain with the hyperconjugative structures. Now this is carbocation. What is carbocation? A carbon which is with positive charge is known as carbocation. So now this carbon is with positive charge. Okay, to balance this positive charge, immediately this is alpha hydrogen. This is alpha hydrogen. This is alpha hydrogen. Because now this is the carbocation. Adjacent to this carbocation, whatever the carbon is present, that is considered as alpha carbon. Okay, now this is the alpha carbon. Upon this alpha carbon, how many hydrogens are present? 3 hydrogens. All the 3 are now alpha hydrogens. Firstly, this bond exists between carbon and hydrogen, moves here. Okay, and neutralizes the positive charge on carbocation. Then we will get carbon, hydrogen, hydrogen, and there is no bond here, H. Because of losing electrons, it will be having H plus. Double bond, C, H, H. Now there is no positive charge on carbocation, that is neutralized. Okay, this is first hyperconjugative structure. In the next step, what happened? One more carbon hydrogen sigma bond is available. So that participates in bond formation between first 2 carbon and hydrogens. Then we will get second hyperconjugative structure. Hydrogen. Now there is no bond between these two. Due to losing electron, hydrogen gets positive charge. Okay, now here hydrogen and single bond, and here hydrogen, single bond, double bond, C, H and H. So this is second hyperconjugative structure, and even third is possible. Whenever the third sigma bond exists between carbon and hydrogen, that involves in delocalization or displacement. Between these two now bond is created. This hydrogen loses electron, then it will be getting positive charge. Hydrogen, C, hydrogen, H plus, double bond, C, H and H. Okay, we got this. And again what happens? Your hydrogen is containing positive charge. So there is no more alpha hydrogen to balance the positive charge on this hydrogen. So pi bonded electrons present between the 2 carbon atoms moves here and make a bond between carbon and carbon. So then the valency of this carbon is balanced, but upon this carbon atom number of bonds decreases, then it will be having a positive charge. Then we will get the final structure. Now hydrogen, carbon and hydrogen, a new bond is created between carbon and hydrogen. Double bond is converted to single bond, carbon, 2 hydrogens on this. Now this is losing electron, so it will be having a positive charge. Okay, it will be having a positive charge. So then we will get this kind of structure. These two are the same structures. So only 3 hyperconjugative structures are possible. So carbocation, this is primary carbocation. Why it is primary? Because positive charge containing carbon is attached with only one another carbon. Okay, upon this carbon only one another carbon is present. So this is primary carbocation. So primary carbocation can give totally 3 hyperconjugative structures. Understand? So carbocation can also be stabilized by participates in hyperconjugation. Clear? Now finally we got these 3. So this hyperconjugation is also known as no bond resonance. Okay, this is also known as no bond resonance. Why it is called so? Because it is almost similar like resonance effect, but there is no bond between the carbon and alpha hydrogen in their hyperconjugative structures. So that we can call it as no bond resonance. Hyperconjugation is also known as no bond resonance. This is very important one. Okay, now we'll see about the stability of carbocations based on the number of hyperconjugative structures. So this is primary carbocation. What we have written here, CH3, CH3, CH2. Okay, separately I have represented all the bonds. So this primary carbocation is containing how many hyperconjugative structures? 3 hyperconjugative structures. 1, 2, 3. Why only 3? Because this is alpha carbon. How many alpha hydrogens are present? 3. Number of alpha hydrogens can give the number of hyperconjugative structures. So 3 alpha hydrogens are present. Possible number of hyperconjugative structures are 3. Okay, now move on to the secondary carbon. What is secondary carbocation? A carbocation are positive charge bearing carbon which is attached with two other carbons. Okay, this is positively charged carbon. Now it is attached with two other carbons. So this is known as secondary carbocation. Okay, now this is tertiary carbocation because this positive charge holding carbon is now attached with three other carbons. Positive charge holding carbon attached with three other carbons, so that is known as tertiary carbocation. Now we have to explain about the stability order of tertiary carbocation, secondary carbocation, primary carbocation and methyl carbocation. So this can be explained based on the number of hyperconjugative structures. Always remember, number of hyperconjugative structures depends on number of alpha hydrogen. Now in this tertiary carbocation, how many hyperconjugative structures are present? How many alpha hydrogens are present? To this is adjacent, so we can call it as alpha. To this carbon, even this carbon is adjacent, we can call it as alpha. Even to this carbon, this is the adjacent carbon, so we can say alpha carbon. Now totally 3 alpha carbons are present. Upon that, each carbon is with 3 alpha hydrogens. So 3 plus 3 6, 6 plus 3 9. Total number of alpha hydrogens are 9. And number of possible hyperconjugative structures are also 9. See the second one. Secondary carbocation. This is alpha carbon, this is alpha carbon. How many alpha hydrogens are present? That is 3 plus 3. Totally 6 alpha hydrogens. Okay, but in this 3 alpha carbons, 3 hyperconjugative structures. Here there is no more alpha hydrogen because this carbon is containing positive charge. Now we can write this structure CH3. Okay, these 3 are not considered as alpha hydrogens. We should not, because they are located on the carbocation. If it is located on the carbocation, that cannot be considered as alpha hydrogens. So here number of alpha hydrogens are 0. Okay, so what is alpha hydrogen? If a hydrogen is present on alpha carbon, here there is no alpha carbon, so number of alpha hydrogens are 0. Among all, which is containing more number of alpha hydrogens? Tertiary carbocation. Okay, whenever number of alpha hydrogens increases, hyperconjugative structures are also increases. So this is containing more stability with more number of hyperconjugative structures, followed by secondary, followed by primary, and least stability is for methyl carbocation. Okay, so in the same manner, even in free radicals, we can explain its stability order. So here I have written different types of free radicals. Tertiary free radical, secondary free radical, primary free radical and methyl free radical. So this is methyl, only one carbon is there, methyl free radical. So now this is the carbon holding single electron. Whatever the species containing single electron or one electron, those are known as free radical. Now on this carbon single electron is present. Now we can say this is free radical. Adjacent to this free radical, whatever the carbon is present, that is known as alpha carbon. On this, how many hydrogens are present? 3 hydrogens. Now these 3 hydrogens are said to be alpha hydrogens. Number of alpha hydrogens are 3. Okay, 3 alpha hydrogens are possible here. Now in secondary free radical, why it is secondary? Because free radical containing carbon attached with 2 other carbons. Okay, so it is secondary free radical. Now the secondary free radical is containing 2 alpha carbons. Total number of alpha hydrogens, here 3 and here 3. So 6 alpha hydrogens. Okay, now tertiary free radical. So this is the free radical which is attached with 3 other carbons. Okay, so we can say it is a tertiary free radical. So this is alpha carbon, alpha carbon, alpha carbon. How many alpha hydrogens are present totally? 9 alpha hydrogens. Okay, whatever the compound with maximum number of alpha hydrogens can give more number of hyperconjugative structures. More is the number of hyperconjugative structure, greater will be its stability. Now among all, this is with more number of alpha hydrogens and it can give more number of hyperconjugative structure and it is more stable than secondary free radical. So now secondary free radical contains 6 alpha hydrogens than the primary. So it is more stable than primary. Now primary free radical is more stable than methyl free radical because no alpha hydrogen is present here. Okay, these 3 hydrogens present on free radical but not on the alpha carbon. So number of alpha hydrogens are 0 in this case. Understand? That's why tertiary free radical is more stable, methyl free radical is least stable. So that is about the hyperconjugation, which is known as another electron displacement effect. Totally 4 displacement effects are there. Inductive effect, mesomeric effect, which is also known as resonance effect. Next, electromeric effect. Finally, hyperconjugation. Even hyperconjugation is known as no bond resonance. Understand? So this is about electron displacement effects. Thank you.